Okay, these are some of my favorite problems because now we get some real life scenarios where we can use this finding the critical points thing. Um, and in most cases, right, you're trying to maximize or minimize something, so you might find more than one critical point and you only use the one that makes sense to the scenario. So the very first homework question, they kind of walk you through it step by step, so that's why there's so many answer boxes. But eventually, they let you just kind of free form. You end up doing the same thing in almost all of them. You set up an equation, take the derivative, and set the derivative equal to zero, because what you're looking for is one of those top of the hill, bottom of the valley points. What I like about these ones, these open top box questions are in all kinds of calc and pre-calc classes, is that there's a little fun like visualizing what that looks like. Because essentially they make a box by like cutting a square out of each corner. And so before it's folded up, it looks something like this. But then after you fold it up, it might look something like this. My not very fancy drawings. All right, so the biggest thing is to label. They tell us a box with a square base, so mine's not very to scale here. What's nice about telling us it has a square base means that this dimension and this dimension are the same. So we can use the same letter, right? We don't have to go like A and B or X and Y. Or on this one, right, it's saying that this distance and this distance are the same since it's a square, not a rectangle, so they have the same two sides. All right, and then an open top, and then they tell us it has to have a volume of 78,732 centimeters cubed. So I'll write that down in a second. So the only thing we don't have labeled on here, right, on a three-dimensional box, there's length, width, and there's also height. So we can call it H or Y. I like when my variables stand for what they are. And notice, like, no matter which one of these you label, the height is this piece that's going to get folded up. So any one of these you could label as H, right? They're all the same. Okay, so then if we're thinking about, they tell us what the volume needs to be. They say the volume, so it has to hold a certain amount. So 78,000-ish cubic centimeters. Think about how you get volume. Volume is length times width times height. But in ours, our length and width, we call them both x, and the height we called h. So it's like x times h, or x squared h. Right? Length times width times height. And so we know that that is equal to 78,732. All right, so then they say first find a formula for the surface area of the box. So here's where our labeling will come in here in a second. Because our whole goal is we need it to hold this much stuff, but we want to use the least amount of cardboard, basically, or metal, or whatever this is, especially if it was metal, since that's more expensive. But we're trying to reduce the surface area, so less material, but it still needs to hold this amount. So, like, what's the best shape for this thing, essentially? So think surface area is we're adding up the area of all of the pieces. And so this inside middle piece, right, is x by x. So this big bottom part is x squared. But then think all of these little flaps here are x times h, because there's a height and there's a length on all of them. So this has an area of x times h, or like this one is x times h, and this one x times h. So all the little flaps are the same size. So if we're trying to add up surface area here, and I'm just using SA as an abbreviation for surface area, but if I'm trying to write down something for surface area, I have the bottom of the box, and then I have four of those little sides. So there's four x times h pieces. And so that gives us a formula for surface area. Now notice right now it's not quite a function. Like in theirs, they want you to do a of x, meaning we want to make it all in terms of x. We don't want two variables in there because we can solve if we just have one variable, but not if we have two. And notice how we saved this equation for later, right? So why did they tell us this? Because now we could get h by itself, right? Divide both sides by x squared. 78,732 over x squared. And so now anywhere where there's an h, we could replace it with this. Meaning in our other equation right here, we'll replace h with something that h is equal to. That's what's going to get it down to just being one variable. So our surface area equation looks like 4x times this 78,732 over x squared. And then we could simplify a little bit, like this x will cancel with one of these ones, and 4 times 78,732 is 314,000-ish. So we got x squared plus 314, 928 all over x. Right, that one canceled, left you with 1 on the bottom still. So there's the part where they're asking for an equation for surface area, or a function, because now it's a function of x. And then they ask for the derivative. Totally up to you, but it's a little bit easier to see product rule if you have it written the other way. So instead of putting over x, maybe we'll put times x to the negative 1, right? It means the same thing. And so that way, when we go to take the derivative of our surface area equation, we have 2x, and then minus, right, negative 1 times this big number, x to the negative 2. All right, so then we have to figure out, where does this whole thing equal 0? So set your first derivative equal to 0 because we're looking for one of those maximum minimum points. And then maybe if it makes the solving easier to see, we can go back to the x to the negative 2 means over x squared. So I'll probably move this negative piece over to the other side. And then we could divide both sides by, or multiply both sides by x squared to get it out of the denominator. Right, get that and that to cancel. We could probably also divide both sides by 2 here in a second. So this 314 number divided by 2. Right, just to try to get that to cancel. So I end up with 157,464 equals x to the third. Right, this one times this one. And then I could take the third root of both sides to get x by itself. Which I'm over here grabbing my calculator because you definitely don't do that by hand. Ooh, it worked out nicely. That's surprising. Sometimes they make these questions so they work out nicely. In real life, that almost never happens. So it looks like the third root of 157,464 is 54. All right, then we have to be careful what they're asking for in the question. So we know the first derivative equals 0 when x equals 54. So that's when that happens. Think about back up here what x represents. X is the size of the bottom of the box. So the bottom of the box is 54 by 54 centimeters. And then we can use the second derivative to check and make sure it's a maximum or minimum. I'll go back to where you had your first derivative and just take the second derivative from there. In fact, maybe I'll just make myself some space here. That way I can fit more stuff on one screen. So the second derivative is 2, and then negative 2 times this 314 number. And it's a negative times a negative, so it'll make it positive 629,856. X to the negative 3. So multiply the exponent down, subtract 1. And the only reason we cared about that was just to double check that that 54 is actually a minimum because we were trying to minimize the surface area, right? Like minimize the amount of stuff we were using. And so if I put 3 into this, so 629, 856 divided by 3 to the third, so divided by 27 gives me like 23,000. So I have 2 plus 23,000, 328. So when I put x equals 3 into the second derivative, I get something like this. I don't really care what the number is. What I care about is that it's positive, which means that it's concave up, which tells us that the point x equals 3 is a minimum, which is what we wanted, right? We were trying to minimize the amount of material we were using. And then they also say, so evaluate what you gave above. I guess that's all the pieces they're asking for. You could also, if they asked for all of the dimensions, it's sometimes nice to go back here and say, okay, well, we knew what the height had to be based on this. So if this is 54 centimeters by 54 centimeters on the base, right? That's what x is. Then the height is 78,732 divided by 54 squared. So that makes the height 27 centimeters. And you could double check that 54 by 54 by 27 actually does give you this volume, which it does. So at the end of these, it's kind of nice to go back and say what all these things stand for, but the open top box problem is a really common one that comes up a lot. But the main framework of all of these is you find the first derivative and set it equal to 0. There's your critical point. And then we also use the second derivative test to make sure that it was actually a minimum and not a maximum. But we kind of had an inkling before we started that it was going to be correct.